So to kick things off, our first keynote speaker is Idit Keidar. And Idit she really does not need an introduction, but still I'll tell you a bit about her. She got her PhD from the Hebrew University of Jerusalem in, what was it, 99? And unmute yourself, just to see that I'm not saying.
It doesn't really matter, but 98.
It was some time ago. And she joined, after a postdoc at MIT, she joined Technion's Viterbi's Faculty of Electrical Engineering, where she is now the Leonard Wolfson Professor. Idit was PC chair for DISC, PODC, and PPOP. This is an order of importance. And she's known as a great lecturer and for her vibrant research group at the Technion. She also heads the university-wide program for excellent students. And Idit will speak about her work on concurrent big data processing. And the floor is yours, Idit. So,
okay, thank you. So I feel like the organizers did a great job in making us all feel like we really are in Freiburg right now. You know, how we all woke up in our hotels this morning and walked down for breakfast and met other people. That was awesome, right? I actually flew in last night and I took a taxi from the airport to the hotel. And at some point I noticed that the taxi driver is kind of scowling at his GPS navigation system. And it was speaking with a very confident female voice, but in German, because this is Freiburg and I don't understand German. So I asked him, what's she saying? And the driver was a little confused by my question. He said, what, who? I said, your GPS lady, what is she saying? And he started laughing, of course. And then he said, you know what? I want to tell you a story. When I got my first GPS navigation system, I couldn't have it installed on the dashboard yet, so I kind of put it in the cup holder. And I pick up this elderly lady from her nursing home to drive her to her daughter's house. And I look in the rearview mirror, I see she's getting settled in, and then the GPS announces, begin driving. She looks up, stares at the car radio, and we start going. And then after a while, we go, and then the GPS shortly thereafter announces, in 800 meters, turn left. And the lady from the back is asking me, how does he know? It was a male voice then. And then we kept driving, and again, the GPS announced something, and again, the lady is asking me, but how does he know? And this went on for a while until she kind of accepted it that he knows. And finally, we get to her daughter's house, and the GPS announces, you've reached your destination. And the lady reclines forward, leans between the two front seats and says, thank you very much. So, the driver and I were like laughing about it. And then this sort of got us talking, kind of a serious conversation about, this is not just the GPS navigation systems that knows where you're going and how to get there, right? There's all these big data systems, all kinds of theys. They know all kinds of things about us, right? They know what you're going to search for, they know what ads to show you, and so on. And so we started talking about this, and just as he dropped me off at the hotel, I thought to myself, funny, because tomorrow morning I'm going to give a keynote about, some mechanisms that are used by all kinds of them to know all kinds of things, collect a lot of information about events in real time and allow us to query them. So that's what I'm going to talk about. Hope I shared the right screen. If not, tell me so.
So while you are doing this, let me just interrupt for a minute to say something about the rules. Everyone can unmute themselves, but I'll stop, or Idit will stop for questions. I'll also be watching the chat and Zulip and whatever and try to collect your questions for Idit. So, but try to keep quiet as much as possible. But if you have questions, Idit wanted to get questions as she's speaking. So
I suppose you do see my slides, right? Yeah, okay. So this talk is actually mostly about a joint project with Yahoo Research. This is based on a paper that we presented in PPOP, the last physical conference took place this February. The first author is Arik Greenberg, my PhD student, and then there's some other authors. Alexander Spiegelman was with Yahoo Research, an intern when he was working on this, and Eddie Bortnikov, Ishkar Hillel, and Lee Rhodes from Yahoo Research, and Hadar Serviansky was working with us at the Technion on this. So it's kind of a big group, and it's really a collaboration of the Technion with Yahoo Research. And so this is mostly what I'll talk about, and then at the end, I'm going to sort of lead into the talk that Arik is going to give later today about intermediate value linearizability. And I'm not going to get into technical details, I'll leave that to Arik, but I'm going to give the context and the kind of a teaser for it. So, but mostly it's going to be in the first one. Okay. So, you know, like I said, we want to down the road talk about real-time big data analytics, you know, all they who know things about us, these systems that allow us to query in real-time information about big streams of data. But specifically, my talk will focus about one of the tools in this big, you know, these systems have a lot of components. The one component I'll focus about is called data sketches, and of course, I'll explain what they are. Specifically, I'll focus on concurrent data sketches, PODSI after all. And basically, the talk is going to touch on two aspects of these concurrent data sketches. First, how to implement them quickly to make them fast, because they need to process big streams of data. And second, about their correctness semantics. And I know some of you are scratching their heads and saying, yeah, correctness semantics. Again, don't we have enough semantics for distributed systems already? So just let me calm you down and just, you know, give you one slide on why I think we actually do need new semantics. We'll get to that later in the talk, but, you know, just to say this is not a, you know, I'm not done in vain. We want semantics that are going to be amenable to efficient implementation in cases where linearizability is too costly, but we want them to be able to provide meaningful guarantees about the error bounds that we get in all kinds of approximation algorithms, and in a way that will leverage our knowledge about the sequential case. So we're going to take something that we know in the sequential case has some guarantees, and we would like to preserve them in the concurrent case with something cheaper than linearizability. And for this, we need new semantics. So, you know, trust me, there's a reason. Okay, but let's go back to our roadmap to big data analytics. So, big data, this is a screenshot of a system called Flurry. It's run by Yahoo, but there are other competitors of other companies as well running these things. And this is a report from a couple of years ago that said that, that this platform constantly gives you real-time reports about billions of user devices and hundreds of millions of applications. And, you know, down the road, we want to look at technologies that support this thing. A little bit of marketing for why this is important. It's not just this one system. There are some market reports that say that this is the biggest growing market. I guess these are pre-COVID reports, but yeah, and you know that a lot of organizations are adopting them. So this is really growing. And in fact, if you look at the web and check out what companies are doing this, then you can see that Cisco is reporting here. I circled this tens of billions of events searchable in seconds, and all these logos down there are logos of companies that use these kind of tools. Well, maybe except the last one. Whoops. Okay. So this is our motivation, right? We want to do big data monitoring, and An indispensable tool in order to do that is data sketches. So let me just tell you briefly what data sketches are. I'm going to give more examples later. So data sketches are a data structure that allows you to statistically summarize a large stream. It estimates some aggregate. For example, if you have a big stream, how many unique elements, how many different users have clicked on your web page, not counting duplicates. Quantiles, for example, what is the average session length or the median session length or the 10th percentile session lengths? What are the heavy hitters? What are the ones that appear most? What are the frequencies of different items? Things like that. And these statistics, these are the things that analytics platforms want to show us. These sketches are very fast. They have a small memory footprint compared to the huge streams that they process, and they're very, very widely used. Where do they fit in the big data analytics world? Well, roughly, very roughly, we can think of it as going on like this. We have all kinds of sources of information that flow into some big content processing pipeline, running whatever on it. And then these streams get stored in some kind of data store, and they also get stored in some data sketch in memory, okay? And basically, this is what we want to focus on, this component that is a data sketch that can be queried by users to get statistics and can be updated from these big stream processing pipelines. And if you're wondering what this little picture is, actually it's been appearing for a while now. That's the logo of the Yahoo Data Sketches library. Okay. So let's do a more detailed example, just to get a grasp for those of you who are not familiar with data sketches, to get a grasp of how they go. So for example, we can have a sketch that's trying to estimate the number of unique visitors to a web page. So for example, let me show you a stream of people and tell me how many uniques there are, I guess. Okay, wait. Okay, how many uniques there are? Just, I guess, raise your fingers, count the fingers to show me. So how many uniques do we have? Everybody count? Yeah. Okay. 4. This is pre-COVID, by the way. That's why they're not wearing masks. So for example, people show up. Some people sign up more than once. We want to know how many of them there are, and that's what we're trying to do to estimate the number of uniques. So the first one we're going to do in order to get rid of duplicates is we're going to hash these people into uniformly at random into the interval 0 to 1. Okay, so once we do that, now we have each one of them once. Okay, if we hash them, and now we can count them, right? Right. Well, except that we have about 1 billion of them, right? So we can't really count them. So how do we estimate how many of them there are without keeping all of them in memory? So that's the basic goal of the Theta sketch, of the sketch called the Theta sketch that counts the unique elements. It defines some kind of a threshold theta, which is a number between 0 and 1. And it doesn't keep all the elements in stream, but only those whose hashes are smaller than theta. So in expectation, the number of elements below the threshold of theta times theta is the number, is 1 over theta is the number of unique people in the stream. So, for example, if I look at the queue and of people standing, and I know the queue is 2 kilometers long, and I count the number of people who are in the first 20 meters, then I know that, if I multiply that by 50, then I'm going to get the number of people in total, right? So, okay. So how do we know what to set theta to? Well, theta defines the accuracy and we might want to change it according to the stream size. So there's an implementation of the Theta sketch that adjusts Theta dynamically. It's called the KMV sketch by Barisef et al., where Theta is going to be the kth minimum hash value that's been seen. Initially, it's 1. So for example, here I give an example with k equals 4. So the first people who come in, Theta is 1, and they're all retained. And then another person comes in, and Theta becomes smaller and smaller and smaller, and you know, eventually, when there are a lot of people, it becomes really small. But we only keep a small number of people. Okay. So this is just one example, but there are many other sketches that the library contains quite a few of them. And typically, these sketches are what is called probably approximately correct, which means they have an error bound of epsilon, and the probability that they have a bigger error is at most delta. Or put differently, they have an error of at most epsilon with a probability at least 1 minus delta. And so they're probably approximately correct. And of course, this depends on the parameters. In the example before, it depends on k, and the epsilon is going to depend on k in some way. And the thing I want to emphasize here is that each of these sketches, there are a lot of them in the literature. Each of them, somebody wrote a paper about it and analyzed its errors, its epsilons, its deltas, whatever. And when we want to look at a concurrent implementation of the sketches, we want to make sure that we can reuse these. Okay, we don't want to start over and do a new analysis just because we're doing a concurrent implementation instead of a sequential. So specifically for the Theta KMV sketch, the analysis by Barisef et al. Goes like this. It kind of shows that it's an unbiased estimator. So the mean is the number of uniques. The distribution over all executions, right? The mean is the number of uniques, and the relative standard error goes inversely proportional to the square root of k, which is the sketch size. And so we get a graph like this. So if we run the sketch many times on many streams, this is the distribution of estimates that we're going to get, with the mean being the accurate estimate. Okay, so that's basically the analysis that we have for the sequential sketch that we're going to work with. So another important feature of sketches beyond being approximate is that they're fast. Why are they fast? Think of the Theta sketch. When it gets an ID, an incoming ID, all it has to do is hash it and compare it to Theta. And then if it's smaller than Theta, it needs to add it to the sketch to find the largest element and to remove it and to update Theta. But importantly, this if has no else, okay? There is no else. So if the element's hash is bigger than Theta, we do nothing, okay? And if the stream is big and Theta is going to be very small, then in the vast majority of cases, we're going to do nothing, okay? So we're going to, that's why the sketches are very fast. They do an if and they return most of the time, okay? So there are more examples. Event counters are a type of a sketch. Quantiles that, for example, give you the duration of the 19th percentile's longest sessions. Something that counts item frequency, countmin. This is an example I'll revisit later in the talk. Heavy hitters, trying to find the most popular items in a stream and stuff. So there's a bunch of them. And just one more requisite motivation slide. I just probably don't need to know this, but we really need to parallelize these sketches, right? Why do we need to parallelize them? Because of the multi-core revolution, which you've all heard about. And right now we're getting performance via parallelism and not by sequential speed. And if we want something to be fast, as we need these sketches to be, we have to parallelize it. And another trend that is pushing for that direction is the fact that DRAM is actually becoming cheaper and it's becoming bigger. And that means we're going to keep more information in memory. So we're going to do more in-memory processing. And the only way to do that, again, is by increasing the parallelism. Okay? Because we're going to bigger demands, and the only way to achieve them is with more processing. So that's sort of to recap the motivation or what we're going here. So what we're trying to do concurrent data structure sketches, like approximate counters and things like that. We want to do them for online monitoring and analytics of big data streams. And we want them concurrent for obvious reasons. And the challenges we're going to have to deal with are having efficient implementations and meaningful semantics. So let's start with the fast implementation, having given the motivation. And what you see here is a screenshot of the homepage of the Yahoo's Data Sketches library. Like I said before, this is the logo, and it's Apache incubating project, so it's kind of pretty mature, and it's very, very widely adopted. So that's why we started. And the starting point for our research when we started working on this was kind of exemplified in this chat in our discussion on issue on the GitHub of the sketches. The sketches are open source, of course, and this is a discussion in the GitHub repository. So there's just somebody who's reporting an error, says, I don't know what this happens, my program crashes, and here you can see the response, the official response of the developer, Lee Rhodes, one of the co-authors of this paper. And what he says is basically, for this to work, if you can read what's underlined here, you must make your sketch wrapper synchronized. Basically, what Lee is saying to the users experiencing problems, no, you can't run this concurrently. If you want to use this code, this library, you have to make sure that it's synchronized. You have to wrap it in one big lock. That's what you need to do. Okay? And this is just one example. This has appeared multiple times. I just showed you one of them. But yes, people were trying to run them multi-threaded because there's a kind of tendency of people to want to run things multi-threaded, and they didn't work. So this is what happens when you do that, okay? This is just a short little experiment that we ran with the library. We take the blue bar is what happens when you just run the data sketches library update only, high throughput, and you get 90 million operations per second. And then you take the sketch in the library and you wrap it up in the lock, just the piece of code on the left, and the performance drops to 30 million operations per second. Okay, why does it happen? Because the lock has a cost, and the sketch is very, very fast. Remember, it's just an if with no else. So this is a huge overhead for it, just checking the lock, even if it's not contended. This is, by the way, single thread. Maybe I didn't emphasize this, but these two results are both for single thread. So the lock is not really needed, but just the fact that it's there slows down performance. So that's a problem. And the second problem is that you can't query the sketch while it's being updated, okay? So the problem I showed before was for concurrent updates. But if we want to do query while updating, we can also use logs, just the same. Or there's something else that sometimes it's done, and that's working in epochs. Basically, you have two data sketches, and while you're building the new sketch from your stream, you're querying the old sketch. The disadvantage of that is that the results that you get are not fresh. You get a delay. You get statistics about the previous epoch, not about the current epoch. They're not really in real time. So I guess that's the time for the enough motivation. That's the time for the drum roll. Okay. If you missed that animation, I got to run it again because I think it's really cool. Okay, this is the data sketches library, and now we're going to make it concurrent. Boom. Okay, so the goals of this project are to allow high throughput by allowing multiple concurrent updates and multi-cores, okay? Harness the power of multi-cores. To allow query freshness, that users will be able to query the data structure that is being updated. And from a system engineering perspective, ease of use, make the library responsible for synchronization, not the users. The users would just use the library as is. And we want to preserve all the benefits of the sketches. We want to make them fast. We want to make sure their estimation error is still small, and we want to keep their memory footprint small. So these are our goals. And the solution is a generic one. It supports any sketch. So you could take your favorite sketch and plug it in. And we're going to take the sketch and parallelize it. Okay, remember this is the picture of where it fits in. I only moved the analytics to the left, so I'll have space to draw on top. But other than that, it's the art. Should be familiar because I've shown this picture before. So what we're going to do is we're going to add some buffering layers. We're going to take this sketch and we're going to partition it. We're going to keep one global sketch and a lot of little sketches, not a lot, but a handful of little sketches that are really buffers, but they're the same sketch, just small. And we're going to buffer updates into the small sketches and then merge them into the global sketch. And for those of you not familiar with these is Maurice Hurley's famous CHIPS notation. So all these little creatures are representing threads. So we have separate threads running and updating different little buffers. We have another thread merging from the buffers to the global sketch. And then we have a lot of other threads that are running queries on the global sketch. One point which is, I'm not going to talk about now, but I'll get back to later. So remember this, is that the queries execute a snapshot. They need an atomic snapshot of the global sketch because it's being updated while they're querying. I'm going to talk more about that later. But for now, let's just keep it a snapshot. Okay. Here's an example. So this is an example. Previous slide showed a generic architecture. This is an example with a Theta sketch and a buffer size of 2. And remember those people, we were trying to approximate the number of uniques. So here they come. Actually, this yellow person hash is above Theta, so he's gone. And then when the buffer is full, right, the buffer size is 2. When the buffer is full, that's when the merger thread starts working. The update thread signals to it, and the merger thread sees the signal, and he merges the local sketch into the global sketch, and then we clean the local sketch. And then they keep coming, and eventually the second buffer fills up, so the merger thread goes and takes care of it. And when it does so, it sees that we have a duplicate, and of course it gets rid of it. So this is an example of how it works. And the question that you might be asking yourself is like, is it still fast? Okay, what about the fastness of it? So we made a big deal of the fact that the sketches are really fast, and we have to preserve this. And the reason they're fast is because of this. Well, before it was an if with no else. Here I reversed the logic, so it's skipped, but the same thing, right? If we're bigger than Theta, we do nothing. That's what makes them fast. But yeah, sure, the Theta in the big sketch keeps getting smaller and smaller and smaller, but the little sketches, we reset them all the time. So what is Theta when the buffer is empty? Okay, if we simply reset the sketch and let Theta, when the buffer is empty, go back to 1, we're going to do a lot of work on the small sketches. And then we're going to do a lot of work merging them that we don't really need to do. So the first optimization we do in order to get this working fast, and this one is really crucial, is that we're missing critical information. We need to know Theta in order to make the local sketch fast. And I just want to point out that our architecture is generic. So it's Theta in this sketch, but it could be something else in a different sketch. But there is some pertinent information that the global sketch would like to communicate to the local sketch. And we built a very light synchronization mechanism where we piggyback this information on the synchronization signal. So we have the synchronization signal where the threads tell the merger that they're ready to be filled, and the merger signals to them that the buffer is empty. And we piggyback this information on that. In this specific case, it's theta, and then this way the local sketch knows theta and uses it to optimize the updates locally. And the other optimization we do is just to exploit the threads better is double buffering, so that when the merger thread empties one buffer, the worker thread can fill another, and then we swap them. So these are the main optimizations that we make. Let's talk about the space and error bounds. So the global sketch is the same sketch that we had before. So it has the same space requirements and the same error bounds and also the same performance, right? As we said before. And then on top of that, we add an overhead. What is the overhead? The overhead is the cost of the local sketches. So each of these buffers gives us B extra space, where B is the buffer size. And on the other hand, it misses B elements of the query. So there's some kind of a trade-off that the error is going to be bigger if B is going to be bigger, if B is going to be smaller, but then the error is going to be bigger if B is going to be smaller, and the space is going to be bigger if B is going to be bigger. So that's the trade-off. I think I got it right, but I'm sure you can figure it out. So this is the trade-off we have, and if the sketch is very big, then at some point this error is going to be very small. But the problem is that we don't always know how big the sketch is going to be. And if you talk to the engineers, they tell you, yes, we have some huge sketches, billions of elements, but we have some, or millions of elements, but we have some small ones with like 5 elements, because this particular, we keep a sketch for each app that we're monitoring, and some apps are not as popular as others, and we don't know in advance. So, we're missing B elements out of 5 out of 1, 1 element out of 1, that's going to give us an infinite error. So we added this this additional mechanism for bounding the error in small streams, which is an eager merge. We use an eager merge with no buffering as long as the stream size is below some threshold, which is defined according to the desired error. So, so this is the code. Actually, the code that's running in the library right now is doing eager merges until the threshold is reached, and then when the sketches become big enough, then it switches to lazy propagation. Okay. So the keys to yes.
A question on slide 34, Isaac Sheff. So I'll read his question, and if you'll want, he'll join again. In the first parallelized example, every incoming datum passes through every little sketches if statement. Is this a speed bottleneck? And if so, wouldn't a single threaded sketch run at exactly the same speed? I'm actually not sure I agree with the question, but yeah.
So the question is because they all go through the global sketch?
Yeah,
No, it's because the way you've drawn the pipeline on slide 34, it looks like every datum passes through the first buffers, the first threads.
No, this is well, I'm sorry if my graphics is not clear, but this is like a demultiplexer. I mean, these are like worker threads grabbing tasks from the pipe, and also in the example I showed, they go to no, where was I? Here. They go to separate buffers, right? So if each one comes in, some of them are grabbed by this one, some of them are, these are multiple threads working concurrently and grabbing work from the shared pipe and taking care of it. Okay, and then the global sketch has less work because they're basically filters. They throw out everything bigger than theta, and they have very few. As theta gets big, they have small number of elements to merge. Okay.
Right. Thank you.
Okay, maybe it's a good time if there are more questions. Nope. Okay. So, so the things that make us this thing work really, really well and get good performance is that we have a very lightweight synchronization. I didn't go into the details of it because it's kind of a flagging mechanism. You guys have seen these before. It's not very surprising, but the point is that the merger thread and the worker thread synchronize only when the buffer is full or empty, which is if the buffer is big enough, is not very frequent, and there are very few fences because they synchronize only in these events. And you get very strong locality here with every thread working on their own local sketch, so they can keep it in cache and it's never going to get evicted. And so it's cache friendly, it's NUMA friendly, and we get good locality. And I think the thing to notice here is that it's almost shared nothing, but not shared nothing, because if we really would share nothing, then they would do a lot of redundant work. So we need to actually share this pertinent information, which in this case of the sketch is the theta. So they really need to know the theta from the global sketch and share this information in order to effectively work separately in their own memories. So kind of a judicial sharing of information that is what we have here. So right? Every worker threads works in its own area, but it gets the theta from the global sketch, so it knows not to waste work, and to, theta can go up and can go down, sorry, and things can become faster. So a graph, even though this is Bati, one have like a few graphs, not too many of them. In the paper there are more. Basically what you see in the red line is the lock-based implementation, and in the blue line on top, our implementation. And in this case, in case of the theta sketch, the buffer size doesn't affect performance at all. So we get the same numbers for different Bs. And then another example that we use our generic sketch for was a quantile sketch. I didn't talk about it, but it's another example that we were in. And what you can see here is that the buffer size does matter. Again, the lock-based is a red line at the bottom, but all these colorful lines, the higher they are, the bigger the buffers. So as the buffers get bigger, performance gets better because the local sketch filters more from the global sketch and does better work.
So we did another question in the chat.
Yep.
Is from Yuda, cannot randomization be used to avoid information sharing?
So the sketch is already randomized, okay, and the analysis already is tuned on theta being, in case of KMV, of theta being the K minimum value, but we need to learn theta as we go along. So yeah, I mean, if the streams processed by the different threads were completely random, probably they could estimate theta instead of learning it asynchronously, and maybe they would get some error. Like they could say, what I've seen is similar to what others have seen, but it would add to the error. It wouldn't preserve the error of the sequential sketch. And I don't know, adding randomization on top of randomization is always tricky. So.
And another question in the chat from Andre is, how would this solution compare to using flat combining? So these are questions you can always ask about any data structure.
Yeah, well, this is kind of a type of flat combining, I guess, because we have the mergers thread that is the single merger thread, and it combines everything in the one thread. So you could say that as a paradigm, this is similar to flat combining, except that we don't combine on every update. We combine we use like bigger filters, right? So we have, each thread has a filter where it accrues a lot of operations, and then the merger combines them in big buffers instead of one by one. If we just had them more fine grained, then it wouldn't work. So I guess it's kind of coarse grained flat combining. Any more questions?
Go ahead, sorry.
Okay, so from graphs to theory, right? So what we want to prove, so this slide is a little technical, but what we want to prove at the end of the day is that the concurrent sketch implementation actually gives us the same bounds or some, if not how close to, or some error bounds that we can quantify. When we know that we have try this again. This is what we want to show at the end of the road, is that the concurrent sketch has some error bounds. Okay, let's put it simply. It has some error bounds that we can argue about and we can guarantee. And to do that, we want to leverage the fact that we know that the sequential sketch has some error bounds, and we want to ask ourselves how much more error is introduced by concurrency and get a formula for that. So in order to do that, we show that, first of all, we have a generic algorithm, not a particular sketch. So we show that when you take the generic algorithm and you instantiate it with something we defined, which we call a composable sketch, which is basically a sketch that supports these snapshots and merges and the things that we need here. So when you take the generic algorithm, instantiate with a composable sketch, I showed two examples, Theta and quantiles, it's strongly linearizable, okay? Strongly linear, if you don't know what strong linearizability is, it's a notion by Golub et al. That is strengthening linearizability in a way that makes it appropriate to reason about systems that use randomness. This is what you need to know, but that's all you need to know for now. So we show that it's strongly linearizable. And strongly linearizable is basically indistinguishable from atomic. So whatever bounds the atomic object, the sequential object has, strongly linearizable has. Of course, when you prove linearizability or strong linearizability, this is with respect to some sequential specification. So we need to give the sequential specifications. Sequential specification is R relaxed. This is another formulation that we leveraged by Hensinger et al. And it's an R relaxation of, so you take a specification and you relax it in some ways. In our case, the R relaxation says that every operation can overtake our other operations. So every query can miss our updates. Okay, and our relaxation of the sequential specifications that you get by looking at the executions of the sequential sketch. So if you take the sequential sketch, you treat it as the sequential specification, then our algorithm is strongly linearizable with respect to an R relaxation of that. I know it's a mouthful and the proof is pretty complicated, but that's the bottom line. This shows that if we can analyze the error of the relaxed specification, then we get the same error for the concurrent sketch. So this is what we do. Yeah, and this is just for illustration purposes. The blue curve is the original sketch, not R relaxed. And our relaxation is because of the buffering, we delay some of the updates. So the query might miss some updates that happened before it took place, because they're still in the buffers and the query queries the global sketch. And so it can only underestimate. And this red curve is the distribution of the approximate sketch. So the approximate sketch, the mean is shifted because we might miss some elements, but the relative error is going to be similar. It doesn't increase the error, the relative error. It's only introduces a constant error. And from theory back to practice, we also ran this. We ran the data sketches implementation and empirically measured the distance from the perfect estimate, which the ground truth, which we knew, for many runs. And this is the distribution of the results. What you can see is on the left side of the curve, it's a flat line. The reason for this is because the x-axis is the stream size, and as long as it's below the eager propagation threshold, there is no error because there is eager propagation. And then once we start to do the lazy propagation, we start to use the buffering, then we always underestimate, we never overestimate. And because this is showing the relative error, which is the error normalized by the mean, it is becoming smaller, the error is becoming smaller as we move on, okay? So we're getting close to the mean as we move on. And these are like the confident, I'm not sure even what quantiles there are or confidence intervals. I think they're quantiles, yeah. Okay, so basically we get, we get this red line. This is sort of this red line, but as it moves, as the stream gets bigger, the mean moves as the orange line moves closer and closer to the blue line as the stream gets bigger. Basically, that's what we see here. Okay, interim summary. I said I'll talk mostly about this, so that finished the part about this. We give a generic solution based on composable sketches. We give a very careful proof based on relaxed consistency and strong linearizability. We get high throughput, freshness, ease of use, everything we wanted. We keep all the benefits of the original sketch. It's fast, the error is bounded, and the memory footprint is small. And one more thing I'm really proud of, even though it's not personally my work, it's thanks to my colleagues, is that this thing is actually part of the Apache incubating open source Yahoo data sketches library, and it's available there, and you can just download it and use our concurrent sketches, and some people are already doing that. So that's really great. But I said I will talk also about semantics, so let me talk about that. And maybe if you've been listening so far, you're kind of wondering why I'm saying that I'll start talking about semantics now, right? I mean, Andrea, she's been listening. Where's Andrea? She says, didn't you just say you proved correctness? Yeah, you know who else has been listening? Hagit's been listening. She says, yeah, you said something about our relaxed consistency and strong linearizability, right? You already talked about semantics. Hi, here's Andrea. Hi. So yeah, but remember I told you I'll talk about the snapshot later? So our proof, this proof of the strong linearizability, it leverages the fact that the queries use an atomic snapshot, okay? The R relaxation, the global sketch is strongly linearizable. The R relaxation is just because of the buffering. If we don't have buffering, before when we do eager propagation, we get the global sketch, we get the error, the strong linearizability with respect to the sequential sketch. In general, strong linearizability requires atomic snapshots. In the theta sketch, this is really, really easy because all you need to know is theta, okay? When you know theta, you got the estimate. But this is not always the case. And now I'm going to show you, yeah, I told you I'd say more about the snapshots. Yeah. So now I'm going to show you an example where this is not the case. So this is a Countman sketch. It's a popular sketch by Kormod and Muthukrishna. And what it does is estimates the frequency of items in the stream. And the way it does it, it uses this table, which is W wide and D long, where W or D deep, where W and D are parameters that determine the epsilon delta that we get at the end. And when an element comes in, what we do is we use D hash functions to hash it, and this gives us locations in all the rows in the table. And each of these rows, each of these locations holds a counter, and we increment all of these counters. So this is what we do. We take here, we increment it, we increment all these, and then what do we return from the query? We just return the minimum of all the counters. So if there are collisions, then the counters might overcount, but they never undercount, and the minimum is going to give us a pretty good estimate. How good? That's been analyzed. And this is the analysis. Again, this is analysis for the sequential sketch that Kormod and core mode and bifurcation did. And if you want to look at one thing at the slide, look at what is in the red box. And it says that if f hat is the estimate, then is the real mean, then the estimate fa that we get is never, sorry, f hat is the estimate. It's never overcounting. It's never undercounting. Sorry, it's always bigger or equal to the real estimate. And it overcounts within at most epsilon times the stream size with probability at least 1 minus delta, okay? And this epsilon delta, of course, depend on the WD, and if you choose WD the way you want, this is what you get. You get that the error in overestimation is bounded with high probability, or with probability 1 minus delta is bounded by Fa plus epsilon n. What happens when you run this concurrently? If you run this concurrently, okay, what we want to do is just read the counters, okay? We do a query for this guy, right? We want to hash him into the table and read his counters, and just read them and return the minimum that we saw. What would happen if we just read it, okay? It might return a value that doesn't occur in any linearization, right? Because it might read the first counter before the first update, the second counter after the first update, the third counter after the second update, and the fourth and fifth counters after the third update. So it's going to see a picture that never took place. It's going to read from the counter something that it couldn't have seen in a sequential run. It's not linearizable, right? This is not linearizable. And similarly, you can construct an example with queries overlapping an update. I'm not going to get into that, which is also not linearizable. The problem is that we require this shared sketch to be strongly linearizable in order to make it indistinguishable from an atomic variable. But this requires an atomic snapshot, which is costly, okay? And this holds for any sequential sketch. But if we look at this one, okay, so the important thing to notice is that if the query atomically happens here, right at the beginning of the interval, which is by linearizability a legal place to execute it, it returns something that doesn't underestimate. We're going to label it FS for start, okay? It doesn't underestimate the real value at the start time. And if it happens atomically here at the end, it overestimates by at most epsilon times n at the end of the stream, the number of updates at the end of the stream with probability at least 1 minus delta, okay? And if it happens in the middle, if it just reads the counters and happens in the middle, it always returns a value between the value it would have returned on the left and the value it would have returned on the right. It always returns something in the middle because all the counters are monotonic, okay? So if we put these three equations together from the last three slides, this is what we get. We get that the value we return does not underestimate with respect to the item's frequency when the query begins. And it does not overestimate with probability 1 minus delta, the stream size, with an error of epsilon times the stream size when the query ends, okay? So it gives us a good estimate, okay? And the error remains bounded even though we don't have a snapshot. And now Yoram has a question. Yoram is asking, okay, fine, okay. So you showed me that this concurrent sketch doesn't, doesn't need to be linearizable, but you're trying to do something generic for any sketch, what does the sketch do need to ensure in order to get the error to be bounded, right? And Jennifer is asking, yeah, can you give something generic that can apply to any sketch? So I guess I have an answer for both of you. Yeah, sure. This is what intermediate value linearizability is all about. It's correctness criterion for quantitative objects that allows you to return any value that is bounded between two legal linearizations. And I think since we're close to finishing, I'm going to leave the details of this for Arik's talk later today. I'm just going to give you, I guess, the punchline of why we want to use IVL in this context is that if we have an ideal, we have an object that for an ideal value gives us an epsilon delta estimate of it, okay? Gives us an estimate that is accurate with probability at least epsilon within an error of at most. Actually, we split it to overestimate and underestimate, but it doesn't really matter. It's a technicality. So with the probability at most delta, it gives us an error of at most epsilon. At least 1 minus delta gives us an estimate of epsilon. Then our main theorem shows that if you take an object like that and you provide an IVL concurrent implementation of it, which is cheaper than linearizability, doesn't need a snapshot, then you preserve the error. You get the same error, okay? So this is why we wanted linearizability, right? Because it was indistinguishable from an atomic object, and then we could preserve the error. So IVL lets you preserve the error for any object that has this epsilon delta property. And that's the motivation for this, but all the details are going to be in Eric's talk this afternoon. And this brings me to my concluding slide. I guess I'm going to stop here. So take questions.
You may do your conclusion slide, just say it again, and I'll let people start asking questions in person.
Okay.
So.
Okay, so just the conclusion is that, you know, big data has big challenges, memory is getting bigger, more data can be analyzed in memory, CPUs are not getting faster, so we need to use multi-cores. And when we do that, when we move to concurrent processing, we face the challenge of how to do things fast, and we do this by minimizing synchronization and sharing pertinent information. But we also need to consider the implication this has on correctness and analyze the impact that concurrency has on the error. So this is, I guess, the big questions that we try to address. And maybe I should say that that we're still working on more sketches and on more extensions to IVL. And you know, this is not the end of the story, but I guess the high level is try to get things to work concurrently that are efficient and correct. That's yeah.
So since we have time, I'll let people ask their questions themselves. So Yehuda, you can unmute yourself and ask.
Yeah, I'm asking, what's the difference or what's the relation between concurrent sketching, as you described, and if I want to do distributed sketching, when the items don't all have to be pushed to one point, but I can start processing them in different points on the internet?
Yeah, so that's a good question, because a lot of previous work actually did distributed sketching. I didn't talk about that, but there was work doing that, and there are two big differences. One of them is the theta, the fact that we share the theta, and so they learn from each other. And I guess that's related to your question from before about how whether we could approximate theta if we didn't get, but there is some shared information here. It's not shared nothing. And the other big difference is that the query can happen in real time. And in all these systems before, they're all offline. They build a sketch, they distribute it, they merge it, and only then it's available for querying. They don't allow queries while it's going on because it's not in one location.
Karen, you can ask your question if you're.
Yeah, so first, thank you for the very interesting talk. Sorry, I can't turn my camera on. Would the parallelism work if we also have deletion of data in the stream? Assuming the original sketch works well, do we get some ordering issues?
Okay, so this is a complicated question because because there are like a lot of different levels where you could answer it. But I think first of all, our architecture is generic. You need a sequential. So for the first part, right, you need a sketch. If your sketch deals with minuses as well as pluses, whatever sequential sketch it is, then so do we, no problem. Okay, we can We can propagate them if we need to do them separately. We can do that. But when we look at IVL, at relaxing the linearizability, we actually, the fact that we can get an efficient IVL implementation leverages the fact that the counters are monotonic. IVL is always going to have the guarantees. I mean, this theorem is always going to hold, but will we be able to benefit from it? That depends on whether we get an efficient IVL implementation. And if everything is monotonic, then we could get very efficient IVL implementations. But if things are not monotonic, then we right now don't know of more efficient ways to do this than snapshots, and we think it might be inherent.
Okay, thank you.
Shai, you want to unmute yourself and ask your question, or?
Yeah, hi. You studied, if I understand correctly, for a given level of errors, can you not decrease accuracy and, on the other hand, increase speed? Did you study the other direction? Let's say you don't necessarily want to increase the speed, but you want to use parallelism to increase the accuracy.
That's good. That's an interesting point. I mean, I guess there's a trade-off between the two, but which the minute you have a sequential sketch that has this trade-off, then I think that's an interesting question. I mean, you might think of implementations that would work at parallel in order to reduce the error, but then they would need to like process the same data or to sample more data if it's a sampling-based technique.
Some of them, I guess, will sample some data and some another, and maybe average there or whatever, or average the data.
Yeah. So I guess maybe that's related to something that we started looking at and is not completed the work yet. But you know, all kinds of algorithms like stochastic gradient descent, which is really popular today. They try to learn, and sometimes there's an issue if you do them asynchronously, and so I guess that's an example where you might, by learning at many places, decrease the error. We're looking into ways to fit that into IVL in order to analyze the accuracy of these types of sort of parameter servers under concurrency, which is a big thing in distributed machine learning, in parallel machine learning today, looking at parallel updates to parameter servers. But yes, good questions to look at in future work.
So next question. Thank you, Shai. Next question is from Jennifer.
Yeah, that was a great talk, Idit. Thank you very much. Does any of the work in this area ever consider faults and kind of like a classic disk PODC viewpoint?
Consider what hierarchy?
Faults. Yeah.
Failures.
Failures?
Failures.
Failures. No, not that I know of, because this is running on a multi-core. So it's shared memory architecture. It's running on a multi-core. We don't really have independent failure. But that's yeah. If you look at this may be related to Yuda's question. If you look at it in a distributed system, then maybe you lose some information if you have a fault. That would be an interesting thing to look at. Yeah.
Thanks.
But you could consider some of these handler threads or whatever, or the merger thread, God forbid, failing in some ways or getting behind or swapped out, or this is not a possible situation.
So in theory or in practice? I think
Whichever you want.
yeah, the worker threads actually are, it doesn't matter if they're slow because they have their buffers, and all the error analysis doesn't assume anything about their progress. And actually the merger thread is, I think the way we implemented it is not a dedicated thread, but it's actually I mean, it depends. We have different implementations. We implemented this multiple times, but one of the implementations, because we have the eager propagation, is to basically switch the merger role between threads. So whenever a thread has its buffer full, and it can try to become a merger thread, but then it doesn't work when there's double buffering. So if you really want to make that, it's not a problem to make it lock free, I guess. Not wait free, but lock free. It's going to be easier to make it lock free.
Okay, so
in practice, this is not a problem because it's running on a multi-core, and it's not like one thread is stopping others because they're all working independently and we're using double buffering, so it's not a problem.
So the timer in the lobby tells me that we are getting close to finishing this session, and actually I don't see any additional questions in the chat or in the Zulit, but if I missed anyone, this is the time to unmute yourself and jump in. If not, I'm sure Idit will follow the Zulip thread or whatever it's called, or stream. These are like beyond me. And I think we take a break now. And so next thing is our first technical session. Thank you, Idit, for a great talk. I see many thanks and compliments for the talk in the chat.